satisfy the criteria that there's a particle in psi 1 and a particle in psi 2. So both states have been filled. But what about this? What happens to this if I interchange 1 and 2? Nothing. It stays the same. Okay? So this is a perfectly good candidate for a boson system. Two particles in the same... No. A particle in state 1, in state 0, and a particle in state 1. And here's how you build it. What about fermions? Can you create a state with a fermion in this state and this state? Yes. All you have to do is put a minus sign here. Okay, can you check? Does that change sign when you interchange x1 and x2? Sure it does. This one goes over to here, this one goes over to here, and the whole thing just changes sign. So yes, you can put, in both cases, you can put a particle into state 1 and a particle into state 0. What you can't do for fermions is put two particles in the same state and two particles, or for bosons, you can. Okay. In particular, let's take the special case of exactly this, where psi 1 and psi 0 are the same state. It's just a special case in which, instead of taking two different states, I take the same state. Okay? So, two possibilities. Psi 0 of x1, psi 1 of x2, plus psi 0 of x2, psi 1 of x1. Boson, fermion wave function. Now let's take the case, as I said, where both wave functions are the same. Well, this just gives me twice the original wave function. All right, it may not be normalized correctly. We may have to normalize it appropriately, but it gives us twice the original wave function, and it's not zero. Nothing wrong with it. Again, it's two bosons in the same state. Perfectly good. But the fermionic construction here gives us what? Zero. So again, we can't make a state in which two fermions are in the same state. The same rule continues if you have multi-particle states. If you have multi-particle states, any number of particles, then the wave function is a function of many variables. And it has the property that for bosons, if you take any two of them and switch them, the wave function does not change sign. For fermions, if you take any two of them and switch them, it does change sign. Again, what happens if you switch twice so that you come back to the same configuration? Clearly, in both cases, nothing happens. Right? So the process of double swap is nothing at all. It's trivial. It doesn't do anything, as you would expect. As you would expect. But the odd thing is that the process of single swap, which you might have thought does nothing, changes the sign of the wave function for fermions. Okay, so that's, if you like, the basis, the mathematical basis, the mathematical set of rules that goes with the Pauli exclusion principle. It can't put two particles into the same state for fermions. Now, what about when there's spin? Well, when there's spin, the easiest way to think about it is just to add another, for each particle, instead of saying the wave function is only a function of position, think of it as a function of position and spin. So in that way, you can think of the wave function as a function of position And let's say whether it's up or down. We could choose sigma z here. Z component of spin. This wave function has the following meaning. Its magnitude, its squared magnitude, is the probability to find a particle at position x with spin either up or down, depending on whether you put in sigma z equals 1 or sigma z equals minus 1. So it's a function of a continuous variable and a discrete variable plus or minus 1. And it represents the amplitude, the probability amplitude for the particle to have a certain location with a spin either up or down. Once you know that, then you say, okay, the wave function for many particles one here stands for the particle, not whether it's x, y, or z. x2, 2, so forth and so on, is representing the wave function for a particle to be at position 1 with spin sigma 1, position 2 with spin sigma 2, and so forth and so on. And now the rule is exactly the same, that if you take all of the stuff that's associated with particle 1, that's both x and sigma, and you take the things which are associated with particle 2 and switch them, bosons, nothing happens, the fermions, spin change, the sign changes. All right, but what it boils down to is exactly what we said in the first place. You simply can't put two particles into the same state, including spin. Including the spin, if they're fermions, you can if they're bosons. Okay, any questions about that so far? Yeah.
You know what this sort of reminds me of a little bit is that you've got a bunch of things and you kind of interchange them. For fermions, then you get a minus sign. So this makes me think about the permutation, the minus sign of the permutations.
These are the representations of the permutation group.
Okay, so that comes into this.
Yeah.
Okay.
Yeah, switching the particles is a permutation, and what happens to them under permutation, a plus or minus sign, defines a representation of the permutation group. Right, that's very definitely has to do with permutations. So it not only reminds you of it, it is it. Yeah.
Particle 1 is side 0, particle 2 is side 1. You wrote that as the product. Why not the sum?
Oh no, the sum of two wave functions is a wave function for one particle. It's simply the superposition of, to build a theory of two particles, the state vectors are the tensor products, are in a tensor product space of the wave functions that depend on two variables. And no, you wouldn't want to add them. Adding them would correspond to putting a single particle into a superposition of states. Right. So right, there's two things you can do if you have two wave functions. You can take a single particle and put it in the sum of the two of them, or you can take two particles and put one in one and one in the other, and for one in one and one in the other, remove the problem. Yeah.
So here we have two particles, and swapping the particles gives interference.
Is what?
Interference effects.
Well, so far I haven't. It certainly does give interference effects, but we haven't talked about interference yet. I may talk a little bit about interference later and the effects of these things.
Well, you've got zero calculating that amplitude square the so there's no probability to reflect that.
Indeed. That's right. You could say the Pauli exclusion. All right, fine. You could say the Pauli exclusion principle is a manifestation of a funny kind of interference where if you put the two particles in the same state and switch them, they interfere. Good. So yes, so it is a kind of interference phenomenon. You're right. Yeah. Yes. Yeah. Because when Pauli was doing it, he wasn't deriving the principle. It was an empirical fact. And he was, if you like, interpreting the principle, finding a mathematical